Okay, so now we did that online activity with, I think there's 21 single displacement reactions. So, um, as much as that was tedious and you're like, oh, I have to write so many reactions, now you are probably so good at them, right? So we're going to switch and look at how to predict what the products are going to be, their state for double displacement. So we're going to do the simplest kind, where you're just going to predict which one's a solid. Then we're going to look at what happens when a reaction will produce a gas, and we'll revisit what neutralization is. Okay? So when we talk about soluble or insoluble, so if you look at the back, the table is called the solubility rules, and then the last column says soluble or insoluble. Okay? Then that means the tendency to dissolve in water. We use AQ to mean soluble. Okay, something dissolves in water, we write AQ. You already know that. So when you have a double displacement reaction, you have to start with two aqueous reactants, and then you let them switch places. And in order for a reaction to occur, you have to get a solid forming. When you have the solid forming, we're going to use the symbol S. So it can be annoying because you might think S means soluble, but we've used the word aqueous before, so hopefully that's not going to trip you up too much, okay? So in order to tell if something is soluble, you have to use the chart on the back of your periodic table. So no, similar to the electronegativity, the activity series, you do not need to memorize it, but you might find that you might be like, oh, I do have some of these memorized, which again, is not my fault. I'm not saying you have to. Sometimes students are annoyed maybe with stuff like this. Okay, so again, try not to push out of your brain things you already know. When we switch, you're going to make a compound, which is a plus and a minus. What is a plus? It's a cation. The anion is listed first, okay? So again, if you forget what acetate is, you might have to go look it up in the polyatomic ion chart, okay? And then many of the ions, the anions, have two rows. Some of them don't. So anything plus the alkali ions, they are listed here. If you forget, your periodic table has it written at the bottom, okay? Then, so anything plus the alkali ions, soluble, so they'll dissolve. And that is why you may have noticed a lot of the times, well, that basically the entire activity you just did was nitrate, right? So nitrate plus anything is soluble. So it's such a common ion because it's small, because it dissolves easily, then it's easy to use, right? So there's a reason why that whole thing basically was nitrate. Anything plus ammonium, soluble. So the ones that are the most soluble substances, the best ones to dissolve in water, are at the top. You might find other versions of the solubility table, that's fine. I like this one the best because it does have like lists like this instead of trying to group them a little bit differently. So then you just have to take a look at what the anion is and then go find your ion. So if, let's say you have one that's got a double row. So if you have chlorine plus, let's say you've got magnesium. Okay, so it's MgCl2. That's something you guys made yesterday, right? Is Mg here? Ag, Pb, Hg, Hg, Tl, Au, Cu? No. So then you go to the next row. any other cation. So what that means is anything else that's positive, and then you can take a look at what it is. So if it's insoluble, you put an S. If it's soluble, you put AQ. Okay? Some of them have a lot of ions. You'll notice there's a pattern, like silver is often not soluble because silver is a big ion, so it's hard to get it to fit in between the water molecules. Yesterday, the solid you made was AgCl2. So if we just kind of focused on observing the types, right? But I could have made you do this. Chloride plus silver makes insoluble. Okay, that's how we got a solid. When you do these reactions, you can't get two solids. That doesn't make sense. So you're going to have two aqueous reactants. You're going to have one solid and one not solid. So if you get two solids, then you've made a mistake. When you get two aqueous substances, then that's no reaction. So again, you have to decide for yourself, if there's 3 questions of double displacement, you get no reaction, no reaction, no reaction. Would I really do that? Probably not. Okay, so then go back and check. So we'll do the same thing like we did yesterday. We'll just check some solids by themselves first, and then we will write a reaction. Okay, so sulfate is number 9-ish, sort of in the middle. So you take a look. Do the first row. We have lead 2 sulfate. Usually with transition metals, it's going to be specific for the charge, so you do have to be careful of that. So calcium, strontium, barium, radium, silver, mercury 1, or there it is, lead 2. Okay? So it says, then you go over, that's going to be insoluble. So sulfide happens to be 10, row 10. So actually there's 2 choices here, right? So ammonium and then sulfide, but maybe you're going to train yourself to always do the anion first, which is fine. But if you look at row number 2, it says anything plus ammonium is soluble, okay? But then if you go to 10, so you check sulfide plus alkali ions, alkali earth ions, or, oh, there it is, ammonium is soluble. So sulfide is sort of unique. It lists the soluble ones first because it's also a very insoluble ion. So silver nitrate, again, nitrate, you're going to see it. It's a really common one to use in these reactions. You might just know, oh, nitrate plus anything, soluble. Or maybe you'll remember that activity and you'll say, oh, all those solutions were nitrates, soluble, right? Silver chloride, we just did that one, but again. So often, I was going to say they're alphabetical order, but I guess not. But a lot of the time, silver is written first, so that's helpful. So 6 is chloride. Chloride plus, there it is, Ag. What is it? Insoluble. Carbonate is all the way down at number 14. So again, carbonate has a huge list of ions there. So carbonates are actually, if you're a worldly scientist, you may have heard of carbonates like chalk is calcium carbonate. So you think about chalk used in a classroom, it's obviously a pretty, chalky substance is often used to describe solids, right? The main component of exoskeletons is a mixture of carbonates, like crustaceans, like crayfish, crabs, stuff like that. So this is a very insoluble substance. So you can see there that carbonate has a huge list of ions. So really you just have to make sure you don't rush and check. So magnesium happens to be the second one, which is nice. So it is insoluble. And then ammonium hydroxide. So again, there's 2 ways to do this. If you go down to 11, it's got alkali ions, and then NH4 is right there as soluble. Or again, you can use row number 2, where anything plus ammonium is soluble. If you forget what alkali ions are, remember your periodic table tells you, right? Okay, that they're group 1, just in case you have a brain fart. And then hydroxide. So hydroxide plus alkali, ammonium, strontium, oh, there's barium, is soluble. Okay, so when you have a double displacement reaction, you have to have aqueous reactants. And when you write the reaction, you can choose for yourself if you trust me that I haven't tried to trick you, which of course I'm not a trickster, right? But you can check that the reactants are aqueous, or you can remember that double displacement has to be aqueous. But now you've got this tool you can use every single time, right? So you can just check if they're aqueous or not. And then you're going to check, do we get a solid or not? And when you have double displacement, because you have 2 compounds switching partners, it doesn't matter which compound you write first. So in this general formula, I wrote this solid second in the products. That doesn't matter. You need 1 solid, 1 aqueous. If you get 2 aqueous substances, then you would put no reaction. So when you were in grade 9, you would have learned that a precipitate is a sign of a chemical reaction. You can see a precipitate. You could evaporate the water and extract the precipitate. Can we see ions with our naked eye? No. So then when you have 2 aqueous substances, which technically means ions in the beaker, right? You guys saw that in that activity as well. Then you can't see anything different, so it wouldn't look like there was a reaction, so then there would be no reaction. If you want, so we wrote in the predicting single displacement section, it talked about some guidelines, like remembering that water is HOH. If you want to write that here, we're going to use, if you have something that looks like an acid, then it will be, or anything with hydrogen really, we're going to use hydrogen as the cation. Okay, so these guidelines, they were written in the, you've written them down before, or had them in your note before. So when you do displacement, whether it's single or double, treat, when you've got a compound with hydrogen, make it the cation. And then when you do that, if you think of hydrogen like a cation, then you can use the table because it says like any cation, right? Then it makes it a little bit easier. So it sort of depends on what your teacher did in grade 10. Maybe they just made you state the type of double displacement. Maybe they used that cheesy dancing partners analogy. Maybe you already had to switch, like you had to predict the products. But usually what I do with these kinds of questions is do everything. So I'll give you the words. You have to write the word equation, then write the one that we're going to do in a second. And then what we're going to do later actually relates to this. So writing total and net ionic. But sometimes with the word equation, it actually helps you see which partners have to switch. Okay? So that's why I like to do it. So if you are, a procedure kind of person, so you want to switch the ions, right? So remember, like displaces like. Or you're going to do like plus minus, always plus minus, plus minus. They're ionic compounds. You can sort of decide for yourself. If you're the kind of person who likes to, you use your brain before you write stuff down, that's okay. You can think about how the partners would switch in your head. and then check out the solubility, or you can write out the products and then literally cross them out like this and write no reaction. That's totally fine, okay? So you kind of have to decide what you want to do. And then again, just remember, insoluble means that you're going to get a solid. Soluble is going to be AQ. And then, of course, if you're writing a reaction, make sure it's balanced. But as you saw, again, in that activity you did this morning, often, for single and double displacement, they're often balanced, okay? Not always, but, or it's pretty straightforward. Maybe you have to add a 2 to get it to balance. Okay, so then the last page is basically just the examples we're going to do. So I really made it small, not to, not to be annoying, but just so that I can fit it all on one slide, okay? So hopefully you can see it on your paper. So it says sodium sulfate, and it says lead 2 nitrate, and it's got the words. So like I said, and I'll be really specific. Part A, write the word equation. Part B, blah, blah, blah. Okay, so I think it's helpful to write the word equation first. And it doesn't matter, even the reactants, you can write sodium sulfate first, or you could write lead 2 nitrate first. It doesn't matter. So I wrote it weird like this, the metal on one line, it looks like, and the anion on another, because I don't want to squish, but also because then it also is easy to see which ones switch. So these are both cations, the sodium and the lead, or they're both metals, whatever you can think of it as, it doesn't matter. So now they're going to switch. And again, it doesn't matter if you write the lead 2 sulfate first, or the sodium nitrate first in the products, it doesn't matter. So these partners, they're the positive, they are going to switch. And like I said, on the test, you're going to get marks for that, so don't worry. And it's like you'll be like, oh, these are the easiest marks ever. Yes. So now comes the hard part. Now we have to write the formulas, crisscross. They're always going to be ionic. Even if we have something like an acid, remember, we're going to treat it like ionic. We're going to do plus minus. And then you can decide if you, right now, if you want to go check, and if you like words better and you want to check and see which one's the solid, or you can do it after you write the formulas. It doesn't matter. Okay, so again, decide how much work you need to show. And like I said, I don't even remember what day, what lesson, but if you write it out, so sodium has a charge of 1, then the sodium over here is going to be the same. So showing the work can then help you crisscross in the products, okay? Sulfate is one of the ones on the back of the periodic table. Lead, it's using the Roman numerals, not its Latin name, so you know it's a 2. And then nitrate, also on the back of the periodic table. So when you crisscross, sodium is a 1. That makes things nice. You don't technically need brackets then, but it's up to you if you want to put them always. This 2 from the sulfate is going to go down here. If you're a bracket person, put them in. So reactants have to be aqueous, and just in case you don't trust me, then you can check. So sulfate is row 9, or actually you could look at number 1 even. Anything plus their sodium is going to be soluble. Or you can go down to sulfate, which is 9, and look at the list. Calcium, strontium, barium, radium, silver, mercury, lead. Nope. So then any other cation is going to be soluble. Now, doing it that way also, you might notice, oh, I see lead on there, okay? So then that's going to help us in the product, right? So you can do them sort of in whatever order you want to. So we'll do lead nitrate. Now this charge for the lead is 2, so that has to cross all the way across. So this time we need brackets. You have to have them. And nitrate is row 3 plus anything soluble. So now that I just did that, right? I just said, oh, nitrate plus anything. Well, okay, sodium nitrate has to be soluble then, right? So as much as when you're first thinking about this, you might be like, oh, this is tedious. I don't want to look this up every single time. It's actually, there's patterns. And then when you do double displacement, they're really pretty simple reactions. So don't try to psych yourself out, okay? So we're going to do sodium nitrate. So now sodium and nitrate are both 1s. We just said it was soluble. And then lead and sulfate are both 2s. And I sort of snuck it in there, but again, you can always check. Number 9, sulfate. Calcium, strontium, barium, radium, silver, mercury. Oh, there it is. There's lead too. And it's insoluble, so that makes it the solid. Okay? If you wrote lead 2 sulfate first, that wouldn't matter, okay? It doesn't matter what order you do it in. Yes. Yes. And you just have to check. So then, again, when you do double displacement, this and this ion, even though it looks annoying, they stay together. So you can say, okay, I need 2 nitrates. So I'm going to put a 2 here. And then that actually balances the sodium. Okay? So double displacement are usually pretty straightforward. I don't want to give absolutes, but that they always are. But okay, so the next example is not as straightforward. So what you're going to see when you get this kind of question is it will say in the question, so get out your highlighter. Oops, that is not what I wanted. That the products are, 2 of the products are water and a gas. So what's going to happen is we're going to do double displacement reaction, and we're going to produce an acid or a base. So acids and bases strong bases have H and O's to make the water. So basically we're going to do atom math, like subtract H2O and see what's left, and that will be the gas. So what I recommend that you do is do the switching like normal double displacement first, and then do the second step to find the water and gas. And the question will specifically say. So we're going to do So sodium carbonate plus hydrochloric acid reacts to produce water and a gas. And I'll even be more specific usually. So if you want to add that in there, and an ionic compound. Okay, so I'm trying to give you a clue. This is a weird reaction. It's going to make water and a gas. Okay, so let's do. I'm going to write it as, I'm going to write hydrogen chloride instead of hydrochloric acid so that it's a little bit more obvious what the ions are, but it doesn't matter. Sorry, I shouldn't have wrote that there, but that's it. In this one, you don't normally have to write um, the word equation, but we can do it here. So sodium sulfate, hydrogen chloride is going to make hydrogen sulfate and sodium chloride. So sodium sulfate was actually one of the ones we already just did. Okay, so we already did this one, but again, we'll do it again. So 2 options. You can do row number 1 or section number 1 is alkali ion. Sodium's in there. That with anything, it's going to be aqueous. Or you can go to sulfate, which is 9. And sodium is not part of the insoluble list, so that means it has to be soluble. This is why, in order to use this table, you really do have to think of hydrogen as the cation or positive. So then you go to chloride, which is 6. The insoluble list is silver, lead, mercury, 1 and 2, TL, silver, or gold, or copper 1. That's hydrogen's not there. So then it's going to be the any other cation, which is soluble. And then when you switch the partners, you're going to get NaCl, which is table salt. And maybe from your own experience, yes, table salt dissolves in water, right? But we also just looked it up. Sodium is always going to be soluble. And then we're going to put hydrogen with the sulfate. But now the 2 here, you have to crisscross. So hydrogen is not on one of sulfate's insoluble list. So it's aqueous. So if you get two aqueous substances, what could you write? Or what should you write, really, normally? No reaction, right? There's no reaction. So that's why the question will say that water and a gas are produced. So this is like step one. All we've done is switch the partners. Then when we're going to do step two to figure out water and a gas, okay? So when it says water and a gas, keep going. Technically, I know I wrote hydrogen sulfate, but if this is aqueous, this is sulfuric acid, right? It's an acid. So if you want to write that. So it really sort of depends as you continue, like not in grade 12, even in future chemistry courses in university. If you have a ruthless prof, they might expect you to do this. Remember that it's an acid, figure out where the water and the gas are. But really, because we're just starting this, I'm going to tell you, it's going to make water and it's going to make a gas. When you look at these two products, you can also think about it logically. Can you make water from sodium chloride? Does it have hydrogen or oxygen? No. Okay? So it's going to stay the same. So this is like step two. And then we're going to do some atom math. So try not to freak yourself out and have a brain fart. Water is always H2O, right? So I'm going to get water. Does sulfuric acid have hydrogens and oxygens? Yeah, sure does. So we're going to subtract. Let's make a little thought bubble over here. So if I have H2SO4 and I subtract, we're going to do some atom math, which is, sure, it's a term for sure. So we're going to subtract H2O, okay? So you can even cross it out, right? H2, gone. 1O, gone. How many are you left with? 3. Sulfur trioxide, is that a gas? Sure is, right? Okay, so it's up to you when you do the water. I'll accept two things. If you write aqueous, that's fine. Sometimes people will be like, oh, dissolved in water, that doesn't make sense. But really kind of it does, okay? If you write liquid, also fine. And then whatever's left from the atom math, that is going to be our gas. You could do the same thing if it was a base. So say it was sodium hydroxide. When you have a base, sometimes the balancing has to be taken care of, which we actually didn't do. That's terrible. So this is definitely tricky. Okay, so the key is to read the question carefully, switch the partners, and then whichever one you can subtract water from. So the ionic compound you're going to make is not going to have H's and O's. You can't get water from that. That doesn't make any sense. It stays the same. And then you just take away H2O, and whatever's left will be the gas. Okay? And the question will say water and a gas. I can't remember if it says ionic compound or another product. So the idea that there are 3 products will be obvious. So when you do neutralization, some reactions, like the one that we use all the time, sodium hydroxide and hydrochloric acid, it'll make a neutral solution. But then when you put, which is fine, but when you put baking soda and vinegar together, which is also acid and base, what do you see? It bubbles, right? Because that reaction is producing carbon dioxide gas. So some neutralizations will make gases and some don't. So then the last one, we'll just do a simple double displacement neutralization. And again, remembering that it's HOH. So if you want to write the water like that, you can. Let's do nitric acid. And so then you get HOH, which is water, and sodium nitrate. So you could, this one is not going to decompose into a gas. What's this called? Sodium nitrate. When we get to the gas unit, or the acid unit, and in grade 12, we'll talk more about like the differences between acids, which sort of leads to why some of them make gases and some don't. But for now, all you have to do is switch the partners and predict what it's going to be. Okay, so the questions in the homework are not as specific. They don't say produces water in a gas, so just be careful of that. If you want to just do the switching partners, that's fine. The the predicting products worksheet definitely has questions more like what I would say. The water in a gas is produced. I think on the last page, I've just starred the ones to draw your attention to the ones that will produce water in a gas. So you can work on both, or you can choose to just work on that worksheet because it is good test review. So what I'll do, because we don't have a super large amount of time, and this lesson is not that long, but you do have to be able to do the solubility stuff, the switching, in order to do that. So maybe after lunch when you come back, you'll just have a little bit of time to do work, and then we'll start the lesson a little bit later, like 12:45 maybe. Okay? Does that seem okay? Amazing. Or if you want to get the morning's activity out of the way, you want to do that first, that's fine too. If you're done, you can just put it in the basket.